Welcome back to another video tutorial where we will be modeling this using Rhino and Grasshopper. Okay, so starting with a point, you're going to want to set a point and then go to your Grasshopper script and say set one point and click your point and hit enter. It's going to take a second to think. And next, what we're going to do is just use the line SDL command in Grasshopper in order to draw a line. And we're going to be doing it in the X direction, but you can choose X or Y or Z if you want. But well, I guess we're doing it in the Y direction. Y direction. X, Y. Okay, we're doing it in the Y direction. The length is going to be 59, and my units right now are feet, so this is 59 feet. You're just going to draw a simple line, and then you extrude that line in order to create a surface. And I use 70 just to kind of get like a rough triangle or a rectangle surface. Next, you're going to use the dimensions command in order to take your surface and plug it into this input. And then you're going to use your Y dimension and your division in order to divide the surface into 2-foot lengths, basically. And then your V into another 2-foot equal length. So in the end, you're going to plug it into this lunchbox command, which under the panels command, there's a lot of different commands you can use. You could just use a square if you want. You could use any of these patterns, but I chose to use the triangle panels B version. So you're going to take your original surface and plug it into the input of that lunchbox command. And you're going to take your subdivisions of panels and plug it into the U accordingly. So just follow your U dimension. You're dividing it by 2-foot panels and the U dimension, and then plug that into your U division here, and coordinate that again with the V division. So U and X basically means X and Y in this way. So it's this length, and then it's this length. So you're just dividing the panels in 2-foot by 2-foot dimensions. So you'll see that this triangle here, or rhombus looking thing, it's a complete square because it's just 2 by 2. So next we're going to deconstruct BREP, and that breaks up our panels. Right now we have right now we have 1,054 panels here broken up along the surface, and we're going to plug that into our deconstruct BREP, and it's going to analyze each of those panels and break it up into its faces, its edges, and its vertices. So we're going to use the edge command, which is basically its curves of each of those panels, which is a triangle panel. So there's 3 line-like curves for each, but as you can see, they're broken up into their own curves. So we want to join those curves so we get one cohesive triangle. And then you create a surface for that. And then we are going to evaluate the surface at the centroid of that surface. So this is your area command. And by getting the area command, you can find the area, like the name suggests, but you can also find the centroid of that area. So basically, each one of these triangles, we find the area of it, and we also find the center point of it. So you find the overall area, and you can find the center point. So you're going to use the evaluate surface command and get that original surface and plug that into your surface input. and then you're going to take the centroid of each of those respective triangles into the point command, and you're going to evaluate that surface in order to get the directions that we want to use to do our subsequent commands. So next we're going to offset this original joined panel, and then we got the curves, we join them. We're going to take this, we're going to relay that into the offset curve command, and we are going to use the frame X output of the evaluate surface and put that into our plane input. And we're going to offset the curves by respective um, distance of 0.25 inches. And this is a command I like to make every time I use feet. You can get inches, and it's basically taking 1 foot and dividing that by 12. So this breaks it up into an inch, and then taking an inch, and then you can multiply that by however many inches you want. So it's really simple. Simple little cluster that you can make to break up feet into inches really quickly. You kind of just copy and paste that from one script to another. Um, so we're going to offset the curves by 0.25 inches to get our little gap in between our panels. And then we are going to offset um, this curve again, but this time we're going to do it by 1 full inch. So in the end, you're getting this. We're going to join that surface and this surface. So now we have two surfaces. And basically the offset was to get that gap there, but then we want to offset it again so that we can get the frame. So one offset was to get the gap in between the frame, and then they get the frame itself, and they get the inset of that frame. And then we're going to use the surface split command to use this surface and this surface. And if you look at them overlapping, basically you can use this surface to trim this surface, and you get a frame, and you get the inside of that frame. So use the surface split command, plug in the larger surface into your surface input, and use the smaller surface into your curves input. Even though this is a surface, Grasshopper is smart enough to evaluate that and turn it into a curve, basically. And you can use that to fragment this into two different surfaces. One will be the frame, and then one will be the inside. And now you want to be able to select each of those. So you're going to use the sort list command, and you're going to, again, evaluate the area and the centroid of each of those two surfaces. And you're going to sort the list by its area. So you're going to take in your fragments, which are all your values, and you can use the sort list command to sort this into a list from least to greatest. So it's going to evaluate the area here of each of those panels, and it's going to use that as a key. That's your input that you're sorting this by, and you can use the output values and use your list length list item command, and it will immediately grab the smaller of the two areas of that. But if we just reverse that, then you can get the larger one. So we're doing that in both ways. We're reversing it to get the larger panel, and then we're keeping it non-reversed in order to get the frame. So now we've broken it up into the inside of the panel and the frame. We're going to use the offset surface command in order to give it a thickness. And now is where it gets a little more complicated. We're gonna take the, I'm gonna skip forward a little bit so you can kind of tell what's going on. But now you think of it in terms of, we've broken it up into a frame and an inside panel, and now we just need to reduce the amount of panels in a certain gradient to get this. So pretty simple. You're gonna get the area of the panels. You're gonna deconstruct the centroid of each of those panels, and you're gonna find the Z component, which is basically just you have an X, Y, and Z number for each of the points of those centroids. You just want to find the Z value. So that's basically your height of the panel. And you want to find your bounds. So that is, the height ranges from zero point 0.6 feet to 66 feet, which makes sense because our height of our surface was around 70 feet. And you're going to use the remap numbers. You're going to plug in your Z component into the value, and you're going to use your bounds into the source target, into the source, and your target is between 0 and 1. And if you do the same thing simultaneously, you take your centroids and you do list length, and which comes out to 1,054 panels or centroids of those panels. And now you're going to randomize this list between 0 and 1 so that it coordinates with the 0 and 1 of the remap numbers. It's now compressed. This list that I just showed between it's condensed it into a list between 0 and 1 because that's our range of these numbers, which is basically like these heights again. And it's randomized that list. It's kind of just shuffle it around. That's what the random command does. So now we're gonna take graph mapper, which if you don't know how to do that, you go to type in graph mapper, plug it in, and it's gonna be blank, but you just right click and you go to graph type, and we're gonna use the Bezier graph mapper. And then you plug in that output into your first command, which is, we're using the smaller than command. So this graph will compress these numbers and make them either smaller or larger because the center of this is positive, and it's between 0 and 1 and 0 and 1. And basically by moving these numbers, it's taking these numbers and it's distorting them to be either between 0 and 1. And when it becomes less than 1, it's basically going to create a list of all those inputs and make an output that is all the numbers that are smaller than that. So now we need to go back to our entire panels and use the col command. So this is our list, and then this is all the outputs that are smaller than 1, and it's a true and false list. So you can see true, true, false. The panels that are smaller than 1 get excluded because of the col pattern. That's what col pattern does. You col out this respective list, which are smaller than, and in the end you get this, and you can manipulate this graph in order to manipulate that list to change the variation of how many panels are less than 1 or greater than 1.